Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Wendy Freedman, who's Professor of Astronomy and Astrophysics at the University of Chicago. Professor Freedman is a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, the American Physical Society, and a Legacy Fellow of the American Astronomical Society. He's a recipient of the American Philosophical Society's Magellanic Prize and co-recipient of the Gruber Cosmology Prize. Welcome, Wendy.
Thank you very much, Gill.
Yeah, thanks for doing this. So our discussion topic today is the Hubble constant. Before we get into the details of it, I want to sort of set the context. So Edwin Hubble, I gather, was a University of Chicago grad, right, in the 20s?
Yes, he was at the University of Chicago, correct.
Yeah, and so could you talk a bit about, sort of the historical context? So his observations sort of threw a wrench into sort of the static universe idea that Einstein had at that time, right?
That's right. So Edwin Hubble, after he left the University of Chicago, in fact, he went to Oxford. He was a Rhodes Scholar, and then he got a job at the Carnegie Observatories in Pasadena that ran the Mount Wilson telescopes. And he first said he was off to war, so there was a delay in him getting there. But when he arrived in Pasadena, he was interested in studying objects that were known at that time as nebulae. A nebula is just the Latin word, it means fuzzy. And these were objects people had been wondering about the nature of. Were they regions in our own Milky Way galaxy where new stars were forming? Or could they be island universes, as it were, outside of the confines of the Milky Way, our own Milky Way, but galaxies in their own right? That word didn't exist yet. And Edwin Hubble began to take photographic plates, that was the detector at the time, large glass plates that had photographic emulsion. And what he found was that there were what appeared to be stars within these nebulae that actually changed their brightness with time. We know these stars, they're called Cepheid variables, and he was able to discover them and in these other nebulae and show that they were well outside the confines of the Milky Way. That is, they were galaxies in their own right. And then he went on, after making this discovery and showing that there were other galaxies, and he found that the closer that the galaxy was to us, the galaxy appeared to be moving with a velocity away from us. And then as he stepped out farther and farther and farther, the galaxies that were farther away were moving away from us at faster velocities. Yeah. And so that led, along with the general theory of relativity that had been developed by Albert Einstein in 1915, to a picture now of a universe that is expanding. And that is, if galaxies are moving apart now, then they must have been closer together in the past. And the farther back you go in time, the closer galaxies, and in fact all matter, would have been. And that, coupled with Einstein's general theory of relativity, led to the picture we now have of a Big Bang universe. That is a universe that began with a very high density, very high temperature, and there was a momentous explosion, and matter and galaxies now have been expanding since that time with the expansion of space. Yeah.
So Einstein's theory, when he proposed it, did it sort of automatically had this feature that the universe is expanding, and he had to do something to make it static?
Yeah, so that was interesting. And Einstein did consult with astronomers of his day to ask if there was any evidence of expansion or contraction, motion of any kind. But at that time, there was no evidence, and this was prior to Edwin Hubble's discovery of galaxies, and so stars are not expanding away from us. The stars we see are members of our own Milky Way galaxy held together by gravity. And so Einstein was faced with a dilemma. He understood that the equations that he had for describing the nature of space and time, as it were, demanded that the universe would either be in expansion or contraction, but it couldn't be static. And what he did to overcome that problem was to add an additional term into the equation, the general relativity equation, the field equations, to force the universe to be static and prevent the universe from expanding or contracting. And then when Edwin Hubble discovered the expansion, he was apparently had said this was his biggest blunder, because he could have predicted the expansion. He knew what his equations were saying. It was demanding that the universe could not be static. And so this quantity known as the cosmological constant for Einstein was simply a mathematical fudge term, in a sense, to force the universe to be static. But he removed it when Edwin Hubble discovered the expansion. And interestingly, in the late part of the 20th century, the discovery was made that the universe is not only expanding, it's actually accelerating in its expansion. And it appears that the term that Einstein later rejected, this cosmological constant, may be correct after all.
Right. Einstein's biggest mistakes turn out to be even the mistakes turn out to be right.
That's right. In a class by himself, even his biggest blunders turn out to be really monumental, perhaps important discoveries.
So when Hubble made these observations, they were pretty quickly well accepted by the astrophysics community, or were there sort of debates and questions around it?
And in terms of the expansion, no, that was pretty broadly accepted very early on. The evidence was pretty clear. The proportionality between the distance to a galaxy and its velocity, despite the fact we look at his data now with the benefit of hindsight, of course, there's a lot of scatter in that diagram, and yet it's clear that there is. That the universe is expanding. That is evidence for the expansion of the universe.
Yeah, so we call it the Hubble constant. It's a constant that essentially defines how fast the universe is expanding. His own earlier sort of measurements were a bit off, right? He was sort of 500 kilometers per second per megaparsecond or something like that.
Yeah, that's right. He was more than a bit off. Right? He measured over 500, and today we measure something around 70. But he wasn't aware at the time that there were difficulties with the photographic plates that he was using. That was the only kind of detector he had available. And they just simply weren't as accurate and precise as the charge-coupled devices that we now have, these linear detectors that we have now even in our own cell phones. And also he was not correcting for the presence of astrophysical dust. And that is, these are dust grains that are formed in the atmospheres of stars. And then when a star at the end of its life expels material back into what we call the interstellar medium, these dust grains, when the light is coming to us, say from a Cepheid variable star, the photons from that star interact with the dust grains along the line of sight to us, and they're absorbed and they're scattered. And so it makes the Cepheid look fainter and appear farther away than it actually is. And if you don't take that into account, then you end up making a large error, which is what happened. The other advantage that we have is the Hubble Space Telescope, named after Edwin Hubble, and we can make our observations now above the Earth's atmosphere. And so we can make, so the atmosphere is turbulent, it's always in motion, and it blurs out the light that's coming to us from distant objects. So we can observe much farther out into the much larger distances than was available to Hubble. And we can make much more accurate observations in the end. Many more objects we can study.
Right. And so from 500 to a constraint of 50 to 100, we reached that level. When did we get to, sort of the range of 50 to 100 to be reasonable for Hubble constant?
That happened in the 1970s. Most of the values that people were measuring were falling in that range of 50 to 100. And we had that situation for a few decades, 2 or 3 decades. And then with the launch of the Hubble Space Telescope, so I and 30 other astronomers, we had what was known as the Hubble Key Project to measure the distances to galaxies using the same Cepheid variables that Edwin Hubble had originally used, but with the advantage of being able to get above the Earth's atmosphere to correct for reddening using these CCD charge-coupled device detectors, and be able to correct for the presence of dust. That was something that my, in fact, PhD thesis was to come up with a technique that allowed you to do that. And so that's how we resolved the factor of 2 discrepancy between 50 and 100 was through the Hubble Key Project and measuring a value of the Hubble constant. We got 72, but for the first time with an accuracy of 10%, rather than this crazy factor of 2 that we had to live with for several decades.
And so we were sort of settling down in the mid 70s. This you said in 1970s, 80s.
Yeah, the 1970s and 80s. A series of a number of different studies in the 70s and 80s that were getting values between 50 and 100.
And the people were sort of accepting it. There is some variance in it, but we can get better and better dimensions, better and better I should say observations that might constrain it better. And then we had a bit of an issue, right? More recently. So in the paper, you say we are at an interesting juncture in cosmology, despite vast improvements in the measurement accuracy of the Hubble constant, most often denoted as H0. A recent tension has arisen that is either signaling new physics or as yet unrecognized uncertainties. So we found, I understand, Wendy, we found different ways to measure Hubble constant, and those different methods are sort of diverging. Is that the problem?
Yes. Another way of getting at what is the rate at which the universe is expanding, which is what we call the Hubble constant, is to look at the background radiation from the Big Bang. And over the last few decades, it's been possible to measure tiny, tiny fluctuations in the temperature of the background across the sky. Yeah. And you can fit those temperature fluctuations, you can fit a spectrum, as it were, to those fluctuations. And though that spectrum is consistent with what we now consider our standard cosmological model. So what is the standard cosmological model? It has not only matter, the ordinary matter that we're used to, the hydrogen, helium, carbon, oxygen, and so on that make up our universe locally, but also a component of dark matter. and that dark matter is believed to be a particle, most likely a particle that was formed sometime around the Big Bang, and it only weakly interacts with the ordinary matter, the baryonic matter that is familiar to us. And in fact, most of the matter in the universe turns out to be of this dark form. And in addition, there is what we are calling dark energy, and that's the component, this cosmological constant, that was originally proposed by Einstein just for the purpose of making the universe static. But the dark energy is causing the universe to accelerate. There's a tension. It's a repulsive form of gravity that is causing the universe to speed up. And in terms of the overall mass and energy density of the universe, it's the dominant component. So our standard model has ordinary matter, a very small fraction, maybe 4 or 5%. Most of the matter being in this dark form, so maybe 25% of the overall composition, and close to 70% of dark energy. And if you have a model of this standard model and fit the spectrum of the fluctuations in the temperature and now the polarization of the microwave background, it's an exceedingly good fit. It's staggering how well that model seems to describe the data coming from the early universe. And given that model, it then allows you to say what the expansion rate of the universe would be at the present time, that Hubble constant. And when you do that for these measurements of the microwave background, you get a value of the Hubble constant about 67. And when we use Cepheid variables, that's what we use for the Key project, and many others have used them in recent years to measure the Hubble constant, then you get something like 73 or 74. And so the real question is, have the uncertainty, so 73 or 74 plus or minus, what is the plus or minus? And do you understand what the uncertainties are well enough? That is, have you accounted for all the potential sources of uncertainty that you can say this is a significant difference? That is, you could have both of those measurements being real. And that there's some missing physics from what we now call the standard model that we haven't accounted for that would explain this difference. Or it could be something having to do with measurement uncertainty. Now
So for my own understanding, Wendy, so the cosmic microwave background based measurements, you say it's an excellent fit with a standard model. Is it the same as the lambda CDM?
Yes. The standard model is lambda CDM. CDM being cold dark matter, lambda being the cosmological constant. That's the term that Einstein added to force the universe to be static. So the standard cosmological model now is the lambda CDM model. That's exactly that's what I mean by standard cosmology, lambda CDM.
Okay, so when you say our measurements and the spectra that we fit to cosmic microwave background, excellent fit, we still don't know a lot about the dark energy or dark matter yet. But are we comfortable with that fit? Because we know the structural features of lambda CDM are well accepted. What we don't know are really the sort of the details of how it all filled up.
That's exactly right. And I think it's a good characterization of where we are in the field right now. And just a few decades ago, we would have said that we understood what the constituents of the universe are, that is baryonic matter that we all know about and are familiar with. And now we're faced with something completely different. And that it appears that the matter that we're familiar with is a very small overall component, and we don't know what the dark matter is. We've been for many decades now looking for signatures of dark matter, doing experiments in underground laboratories around the world, trying to see if you can detect the effects of dark matter as as in the nuclei, for example, of germanium or silicon. And we've been using gamma ray satellites to see if there could be annihilation signals that could give us some hints about what the dark matter is. There are accelerators, for example, CERN in Geneva, and you look for signatures of what might be a dark matter candidate, in its interaction with other particles, and so far it has not been possible to find evidence to directly detect the dark matter, looking for axions and so on, and then the dark energy, perhaps even less so. We really don't understand what the nature of the dark energy is. So yes, I think it's an absolutely fair question for us all to ask. Okay, we don't understand yet in detail what is responsible for this standard model that seems to fit the data so well. So it wouldn't be surprising if something is missing. And the way that you would find out if there's something missing is to measure the Hubble constant locally very accurately. Because if it doesn't agree, that may be telling you something about your standard model and that you don't yet understand. And you would have no other way of getting at. So that's why we're so excited about this, and why there's been so much effort to try and understand, okay, how could we explain this in terms of the physics? And I don't know how many hundreds of papers now have been written on the subject, but many people are trying to come up with ways that could potentially explain this discrepancy. So far, nobody has found anything that looks plausible or reasonable. And one of the difficulties is that if you change things to fit the Hubble constant measurement or explain that discrepancy, then you ruin the agreement somewhere else. Right. So, I mean, what's interesting is in the case of dark energy, there were many things we didn't understand at the end of the last century. We didn't quite see how large-scale structure would form if there was only the matter that we knew about. If you ran numerical simulations and tried to match what we see on the largest scales, distribution of galaxies and clusters, it didn't work unless you had some form of dark matter and dark energy. Unless you had this contrived situation where you had only matter, but not the density that would require the universe to be stable. We could go into that more. I don't want to go into that detail too much, but and also there was a discrepancy of the age. If the Hubble constant was high, at the high end of the range of 50 to 100, that would lead to a discrepancy with the ages of the oldest stars in our Milky Way galaxy. And you can't have stars that are older than the universe itself. And so when the acceleration was discovered and the evidence for dark energy came in, it solved all those problems at the same time. It was interesting. All these very different kinds of issues were solved when you allowed for a cosmological constant or something like it. Now, if you try and solve the Hubble constant problem, it gives you a problem somewhere else. And some people have found things that work. You might get a Hubble constant of 70, maybe even 71, but nobody can seem to find a model that gives you 73 or 74. And to do that, to increase from 67 to 70 or 71, it requires a lot of fine tuning that makes people uncomfortable that you're just adding the physics to explain this problem, but you don't understand what would motivate the physics that you're adding, and then you have to have the effects disappear so that you don't affect this spectrum that I've been talking about for the microwave background. So it's a puzzle, and right now we don't know how it's going to resolve. We just don't know.
Yeah, it's exciting. So when we use the CMB, we are looking back in time, fairly close to the Big Bang. And the other method, the Cepheid variable star based method, is sort of local, right? And so the local observations give us close to 67. The CMB gives us in the mid 70s.
The other way around. So
that's around. Okay, so the Cepheid gives us 70, mid 70s, but the CMB gives us 67.
That's right.
Okay, and so people might think that these numbers are close enough, good enough for government work. But the problem, I think, is that if you look at the 3 sigma range of these observations, they're not overlapping anymore, right? That is the biggest issue.
That's correct. So if the error bars that are being quoted are correct, this is a very significant difference. And so in a funny way, we're talking about the error bars on the error bars. Is there something that we're missing? And that is not unusual in science. When you're trying to make a measurement, it's essentially the things that you don't know about. You have no way of correcting for or allowing for, because you simply don't know about them at the time. And there are lots of examples of those in astronomy. So that's why you'd like to make measurements in very different ways. And that's one of the things that my group and I have been doing for the last several years is to measure distances to galaxies that are completely independent of the Cepheids. Because if there's a systematic error in the Cepheids, we could make the measurements over and over and over, but we'll never detect it because it's just something that is intrinsic to that method. And the way you could uncover if there's a systematic error is to do things in a completely independent way. So we've been using stars called red giants to measure the distances to nearby galaxies.
We'll take a quick break, Wendy. When we come back, we'll talk in more detail about the new method.
Okay.
Thank you.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.
So we're back. Wendy, we were talking about the Hubble constant. It's something that was proposed by Edwin Hubble in the 1920s, which gives us an idea how fast the universe is expanding. And over the years, better measurements, better observations have given us, a better precision as to how much that Hubble constant is. And things were settling down in the 70s and 80s to that constant to be in the mid-70s. Our technology got better. We found different ways to measure it. And now these different ways are sort of diverging. And the sigma bars, error bars around them, because of better technology, they have shrunk as well. So now we are in a position that the measurements are not, at least the error bars are not really overlapping. And that is an exciting thing because it possibly indicates there is some new physics there might be, or we have to think about this in a slightly different way. And you have been looking at this problem from a slightly different angle. So you have a paper, the Carnegie-Chicago Hubble program, and independent determination of the Hubble constant based on the tip of the red giant branch. Are we talking about the red giant stars here or something different?
Yes, we're talking about the red giants. And I'll just say that it was in the early 2000s that the value of the Hubble constant settled down to a value of about 70. Yeah. And then, yes, as it's become possible to measure these distances with higher and higher accuracy, we now find ourselves in this place where we have this discrepancy. So we're using these red giants. Our sun will eventually become a red giant. These stars are essentially the mass of the sun or smaller. And as they go through their evolution, our sun right now in its central core is fusing hydrogen into helium, burning hydrogen into helium, we would say. And when that hydrogen fuel is exhausted, the star begins to contract, but it's not enough. The temperature is not high enough to start burning helium. In a higher mass star, you can start to burn helium.
Yeah.
But the temperature is not high enough. So that occurs, the hydrogen into helium occurs in an envelope surrounding the core. And the temperature keeps rising. And it does so for the reason that the central part of the star is what we call an electron degenerate core. And it doesn't have the ability to expand and cool the way it does in an ordinary star. So the temperature keeps rising until it reaches about 100 million degrees. And then there's an explosive flash, a so-called helium flash. And then the star can burn helium in its core. And when it does that, it settles down to a lower luminosity. Okay. So how we use these stars as distance indicators is we look for these stars in the halos, as the outer regions in nearby galaxies, many of which have Cepheid variables, the same galaxies that we've looked at for Cepheids, and they don't reach any higher luminosity than they can achieve before they have this helium flash. So it's like a sharp edge when we go and look at the distribution of brightnesses of these stars. We see them at all brightnesses up to the point of the helium flash, which makes it a very, very precise way of measuring the distances to galaxies. We go out, we survey, we find these stars, we look for the point at which they don't get any brighter, and then we can use stars in our own galaxy, as we do for Cepheids, where we know the absolute brightnesses of these red giants, and then we can determine the distance via the inverse square law of light. It's essentially the same technique as we use for Cepheids, but slightly different physics and background to them.
But these red giants are really big, right? Is Betelgeuse a red giant?
Betelgeuse is a supergiant. It's even bigger.
I understand that is the diameter of Betelgeuse is like the orbital diameter of Jupiter or something like that.
Yeah. These supergiants are even bigger than the giants. Aren't these creative names astronomers have come up for these stars? But when our own sun becomes a red giant, in fact, the oceans of the world will boil as the atmosphere of the red giant engulfs our planet. So that our sun is about halfway through its evolution. It's about 4.6 billion years old right now. We don't have to worry about this in the near future. But if we do survive another 4.6 billion years, we will have had to have solved this problem, because our own Earth will not be a hospitable place to live when our sun becomes a red giant.
It might become the sun's diameter, I gather, is going to be close to the Earth's orbit, right?
Mm-hmm. Yes.
Yeah, so we probably have no chance unless we can move the planet elsewhere.
That's right. We will have had to solve the problem of where else to live long before that. But in terms of the existence of human beings, relative to the 4.6 billion years of the evolution of the solar system, it's a very, very small fraction indeed. So that we have a long way to go.
So we're using these red giants. So when we look out, what's the frequency of these things that we find? In other words, if we look at, say, 10 million light years out, how many red giants will we find?
It's not unusual to find thousands of these objects, in some cases even 10,000. It depends. So, of course, the density of stars falls off as you go from the center of a galaxy outward. And so we optimize the fields that we observe using Hubble to avoid the inner parts of the disk where you have a lot of overlapping stars because the density is so high. And we don't want to go too far out, so there aren't many. But say thousands is what we typically would find.
Thousands. And what is the distance range we are looking at?
So we're looking out to, I'd say, extremely reliably out to 20 megaparsecs. We can get distances of a couple percent. We can go to 30 megaparsecs, so that's roughly 100 million light years. With uncertainties of 5%, maybe 7%. And with the James Webb Space Telescope, which is due to be launched in October of this year now, we can go out to 40 or 50 megaparsecs.
And so the idea here, Wendy, if I understand it correctly, just like the Cepheid variable stars, there is a mechanism here that allows us to determine distances.
Yes.
And yeah, how does it work?
So what we do is we measure the luminosity of these stars in the halo. What we know is that, our ordinary experience, if we look at a light nearby, say a lamppost, and then we look at a lamppost in the distance, the more distant lamppost is fainter. And it's just a property of light that the luminosity or the intensity of that light decreases as the square of the distance from us, right? 1 over the distance squared. That's the inverse square law of light. So if we know the wattage, as it were, the power that's coming out of the lamppost nearby, we know how bright the lamp actually intrinsically is, then we can see how what the luminosity of your lamppost in the distance is. And by comparing those, we know that the luminosity drops off as the square of the distance. We can measure the distance. It's that simple. And so the trick is to determine the wattage. And we do that by geometry, literally high school geometry. We observe stars that are in our Milky Way galaxy nearby, and we observe them at different parts of the orbit of the Earth around the sun. And if you put your hand, you hold your arm out and you look at, say, a finger that you extend, and you alternately blink with your left and your right eye, the position of your finger changes depending on your vantage point. And we use that, it's just a measurement of angles, and we can determine the distances to nearby objects. So we determine the distances to these red giant branch stars, we determine the distances to these Cepheid variables. And there are other techniques that are also based in geometry that are independent of those. So we have several different ways of doing that. And essentially, we're establishing the wattage of the objects we're using, both the red giant branch stars and the Cepheids. And then when we observe those objects in distant galaxies, we see how bright they are. We apply the inverse square law of light. We determine the distance. And
so I know that there's some type of supernovae that are considered to be standard candles, right? Are we using those in this exercise?
Yes, we are indeed, because the Cepheids and the red giant branch stars can only be applied out to distances of somewhere between 30 and 50 megaparsecs. And the difficulty is that because galaxies interact gravitationally, they induce motions in their neighbors. We call those motions peculiar velocities. And essentially what it is just noise above the Hubble expansion. So Hubble told us if a galaxy is at a certain distance, it's moving at a certain velocity, but there's scatter in that relation, and it's real. It's induced by the gravitational interaction amongst galaxies or clusters of galaxies. And so as you go farther out in distance, where the expansion velocity gets larger, right, it's proportional to distance, then the peculiar velocities, which are maybe 200, 250 kilometers per second on average, they're a much smaller component of the expansion velocity at larger distances. And that's where the supernovae help you, because the supernovae are much brighter than the Cepheids or the red giant branch stars, so you can observe them much farther out where the peculiar velocities are not significant. That said, the supernovae give you relative distances only. It's like the lamppost that I described. You can see that the ones that are more distant are fainter, but you don't know the wattage of the nearby ones, because there aren't any supernovae, for example, in the Milky Way, where you can use the geometric techniques that I described, the parallax measurements. Yeah. And so what you use are red giants or Cepheids. It's like an intermediate step. We can get the wattage of the Cepheids and the red giant branch stars, and we measure the distances to galaxies in which these type 1a supernovae have happened. So that gives you the wattage of the supernovae, and you can extend farther out into the universe. So it's essentially 3 steps: the geometry, then we use Hubble to measure Cepheids and tip of the red giant branch, And then we use supernovae to go out into the distant universe, but we're overlapping at each step.
In all cases, do I understand it correctly? In all cases, we are using luminosity as a way to approximate distances, right?
Yes, the measurable that we have is the luminosity of the star. Yes.
And so are there any, sort of, if you just think about, sort of systematic errors, are there any possibilities there in terms of, since it's all sort of connected all together, if you miss something, it's going to affect everything, I would imagine.
You bet. And this is literally what does keep me awake at night. It was the basis of the key project that we did in the 1990s, early 2000s. The design of that project was to try and beat down the systematic errors. And we do know about the existence, for example, of astrophysical dust. And that's where people like Edwin Hubble and others who followed went wrong systematically, is they didn't correct for the presence of that dust. They couldn't. They didn't have the detector capability of doing it, and they were stuck. Right. And so we're using, for example, the Cepheid variables. They are young stars. You find them in the disks of galaxies close to where they formed. So there's dust there, and there's their atmospheres have dust in them depending on the chemical composition of the star. And we don't exactly know what the effects of, we can empirically try and put limits on that, but we have to worry about it. And then, as I mentioned earlier, one of the reasons why we went to the red giant branch stars is that they exist in the outer halos where the density of stars is lower. The Cepheids, you're in the disk, and so you get overlapping of stars when you're trying to measure the luminosity. In the halo, literally, you can just see your star is isolated. So you put an aperture around it, as it were, and add up the light in that aperture, and you've got the luminosity. We actually do it in a more sophisticated way, but in essence, that's what you can do. And then for the Cepheids, in your aperture, you have many overlapping stars, some of which are redder than your Cepheid. It's making the Cepheid look redder in color. And so you have dust, which makes the star look redder. You have the chemical composition, which if it's high will make it look redder. And you have the overlapping or the crowding of images. So I do worry that all those three effects are working in concert, and you have to have very precise measurements in order to disentangle those effects. And so those are the kinds of things we're looking at in detail and trying to understand. Is there something that we haven't yet been able to measure, to show unequivocally that there is not a problem, right? Yeah. If we can take these error bars at face value, we're learning something really interesting about the universe. But if there's still something that, just because these things are hard, these are not simple measurements where we can go into a laboratory and make the measurements over and over and change the experimental conditions. We have astrophysical objects that are at great distances that, they're faint, and so these measurements are not trivial. So that my own personal view at this point is that we still have more work to do, and it'd be great if we could find new physics. It'd be extremely exciting. And if we're going to make an extraordinary claim like that, as Carl Sagan said, you have to have extraordinary evidence. And so we're working hard to try and provide the extraordinary evidence one way or another. And it's important, either way it turns out. The
source of error, if at all it exists, has to be ordinary matter. Right. What I'm asking is, there cannot be a source of error from, let's say, dark matter. I know WIMPs have been suggested as a candidate for it. Is there any possibility that the dark matter could, weakly interact with any of those measurements?
No. this kind of measurement would not be affected. If people have looked, for example, if you have weakly interacting massive particles or WIMPs in the centers of Cepheids, could they have an effect? No, it's just not a big enough effect to be observationally important for the type of measurement that we're carrying out. It's more likely to be something having to do, for example, with the chemical composition of the star or the evolution of the star, right? These stars are changing their characteristics as the Cepheids we didn't talk about in detail, but the atmospheres of Cepheids are in motion. They're actually pulsating. And the stars are moving to hotter temperatures and colder temperatures. They sort of looping back and forth in luminosity and temperature during the course of their evolution. And so it may be that we just don't yet have that the stellar evolution and the effects of that evolution on the star, if you're trying to make a 1% measurement of the Hubble constant, which I should say the microwave background observations now are at a level of precision of 1% or better. We're not there yet with the local observations. There are too many astrophysical effects that preclude that kind of accuracy. So I think we have work to do, those of us who are making these measurements based on astrophysical objects, to demonstrate that these other kinds of effects have been brought down to a level where we can say with certainty, okay, this is a measurement to 1 or 2 or 3% or whatever the number is, and that's a significant discrepancy. And so there are those who argue we're already at the 1% level, and this is not even 3 sigma, but 5 sigma. And I think that's premature. When I look at the data, that's just not what I see. And I think we have a lot more work to get there.
Yeah, I mean, good thing is we can only go forward from here.
Yes.
Measures can only go better.
Well, and the good thing is so there's a European satellite called Gaia. It's making measurements, these parallax geometric measurements that I mentioned earlier, for 1.8 billion stars in the Milky Way galaxy. And some fraction of those measurements, of course, are Cepheids and they're red giants, and there are other kinds of stars we use that I haven't even gone into. But so our group is working on different stars again to try and get at these issues of systematics, because they'll be different for each kind of object. And if we can get the statistical uncertainties for each measurement down, then we can compare them, and then we can have some confidence in the overall systematic uncertainty. And so those measurements are getting better. The James Webb Space Telescope is due to be launched. It is sensitive in the infrared, and so we can minimize a lot or decrease, have smaller uncertainties because of dust and metallicity, chemical composition, things that I've talked about. And even with Hubble, we still have objects that we can observe and get our statistical uncertainties even smaller. So I'm very optimistic that we're going to settle this in the next few years. There's just so many new capabilities that are coming online that are going to let us really get to the bottom of these current uncertainties, and we'll see. And if there's new physics, that would be very exciting. But let's hear.
I don't know if I understood this correctly, Wendy. There was some speculation that potentially one way to explain this is that we might be in a little bit of a local bubble when we measure these things, as opposed to the entire universe. Is that pure speculation or something that has some credibility?
Well, in the 1980s, when we were still in this factor of 2 uncertainty, that was, I think, a real possibility, that somehow we're in this low density bubble, and that we just appear to be expanding faster into this local bubble. But overall, on average, the expansion rate is actually lower. But now that we're at as I said, I don't think we're now at 1 or 2%. But in terms of relative distances, for example, with the supernovae, we now have samples, in some cases, there are 1,000 supernovae or more. And the scatter in the Hubble diagram is very small. And so if there were these bubbles, we would see that in the scatter. And and we don't. And even in the fluctuations in the microwave background, there are limits, to what on the largest scales a bubble could be. And so I think that's very unlikely. I think it's very difficult to get small, really small scatter coincidentally, right? It's easy to get measurement errors increase the scatter. And so as the data have become more and more precise and the samples have become bigger and measurements, particularly of the type 1a supernovae, there's just not room to explain this discrepancy with a bubble. Doesn't work.
So where are you from the Carnegie-Chicago program, the tip of the red giant branch idea? Do we have some measurements from it? Where do we come out?
Yeah, well, that's the interesting thing. I think our hope was that we would either find that our results were in agreement with the microwave background or with the Cepheids, and we landed essentially in the middle. So,
that's actually.
Yeah, the microwave background measurements are at about 67 and the Cepheids are 73 or 74, and we're just under 70, 69.6. And
so, the error bars are not overlapping anymore?
Well, our error bars actually agree quite well with the microwave background. So if, I hadn't spent the first couple decades of my career working on Cepheids, I'd say, we didn't have the Cepheids, there'd be just no discrepancy at all. To within the measurement uncertainties, they agree. And in fact, the red giants agree with the Cepheids also reasonably well. They're in the middle and they straddle the two. So we've uncovered a second tension, as it were, or discrepancy. One is between the Cepheids and the microwave background, and the other is between the Cepheids and the tip of the red giant branch. And so that's where I think our focus is the next couple of years. And this past year, we've just finished two very major studies to try and test our calibration of the red giants. And it's holding up. Those two different measurements to 1% agree with the paper that we published last year that you referenced. And so we don't see a problem in the calibration. That's the wattage end of things, measuring things locally. Where we suspect the difference is right now is in the range of distances that we're covering with the Hubble Space Telescope. And so that's where we're focusing our attention now, is to try and understand where is that discrepancy arising, and do the issues, for example, I mentioned the reddening by dust and the chemical composition and the blending or crowding of stars in the Cepheids. Is that an issue? Could it be a systematic effect? And so that's what we're trying to understand right now.
It makes sort of intuitive sense, right? Since you landed in the middle, could one say that sort of shows that we haven't quite gotten the systematics or the measure of the errors correctly? And if we measure the errors more precisely, perhaps it's all going to overlap.
It could go either way, but I think you're characterizing it correctly, that we don't yet have, that there are issues with the uncertainties that, could eventually you would end up in one place or the other, right? Because we still overlap with the Cepheids. It's saying, but where I agree with your statement is, if you're underestimating your uncertainties, that translates directly into saying that you have a larger, if it's a 3 sigma uncertainty with the microwave background. So the discrepancy with the red giant branch stars, I think, really is indicating that the Cepheid uncertainties have been underestimated. But as I said, there are many things we can do now to improve those measurements. And I think this is not going to take a long time. It's not going to take a century, as with Hubble, to resolve. This can be, I think, in the next few years, it can be resolved.
Yeah, I would imagine a lot of people are holding out that it's not going to resolve because it'd be less exciting.
Yeah, well, it's true. I think parts of all of us probably want there to be something completely new and unexpected. But as I said, if you're going to claim that, then you really better have data that you see as as bulletproof. And to get there, I think we have a lot more to show.
And so in conclusion, Wendy, if you look forward 5 years, both in the program, the Carnegie-Chicago program that you mentioned, as well as other things going on, where do you think we will? Let me ask you differently. What are the things that you're most excited about in astrophysics?
You mean independently of this one?
This one and anything else that you really think that we might make a big leap toward?
Yeah, I think, well, I am really excited about this one. I think we have the prospect of learning something really new and exciting about the universe. I think what we have coming online in the next few years with JWST, we're going to probe back into the earliest moments of formation of galaxies and black holes and supernovae in the universe, and to have the opportunity to study planets, exoplanets, that are similar to the Earth, have similar masses and perhaps chemical compositions that could be actually measured in the atmospheres of these stars that could be signatures of life. So one of the things that I did before coming to the University of Chicago, for 12 years, I led the project known as the Giant Magellan Telescope, which is a 25-meter telescope to be built in the Andes Mountains in Chile. And one of the things that it will do is have the capability of looking for planets that have chemical compositions that might be biosignatures, evidence of life. But I think what also really intrigued me was the possibility that with these new facilities, like the James Webb Space Telescope or these giant telescopes that are being built also on Earth, that you discover things you can't even anticipate now. Just questions you don't even know how to ask. And so I think the era of these giant telescopes is going to be a very exciting one, and one that I'm really looking forward to.
Yeah, I don't know if you saw this, as part of the COVID-19 bill, somebody put into that bill that the government has to release all information on extraterrestrials. And so we can probably shut down many of these programs because we're going to find that they have been here for a long time.
Great. I look forward to that.
Excellent. Yeah, thanks so much for spending time with me.
My pleasure. Thanks for having me.
Thank you.
Okay. Bye-bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.